This one, because of, just so it works better, we are going to use some kind of pre-filled notes a little bit. These are in the notes folder on Blackboard if you want to follow along. Otherwise, they'll just be there as we save it. All right. So let's look at some ionic compounds. We talked about ions last time and making these charges. So how do we put those charges together? We just have to make sure that we can build the appropriate compounds so that they are neutral. So ionic compounds should be generally neutral, or at least we can be more general and say the sum of the ions charges must add to the overall charge. So what does that mean? That means if we want to make a compound of sodium and chlorine, and this is a pretty easy one, you can probably figure this answer out already because of what you know, but let's just go through it as though it was something we didn't know. We first need to determine the charges of the ions. Remember, for some of them that's easy because they always have the same charge. So sodium is one of those. What is its charge always? Always +1. So the ion is going to be always +1. What about chlorine? What's its ion going to be? -1. So we first determine the charges. And then what do we do second?
This might be a stupid question, but how do you know the charge?
For some elements, they're always the same because of where they are in the periodic table. So group 1 is always +1, group 2 is always +2, group 7A is always -1, group 6A is usually -2. So there's some rules there.
That we like memorize it, it's not written,
right? Right. We'll talk later when we get into electrons how you can figure that out from the electron counting. But for now, it's most useful just to know those. Yeah. You can think of it as with those at least adding up to 8. So like the ones in 7A want to add up to 8, so they have to add one more electron to get to 8, and that makes them -1. This is like however you want to remember it. But yeah, all the ones in the middle we don't know like that. So we have to be told what the charge is because they can have different charges. So once we determine the charges, we can match the ions together so that the overall charge is, in most cases, neutral. So if we want a compound between sodium and chlorine, we need to add those charges together so that they're neutral. And that means that we only need one Na and one Cl because we've got a +1, -1, so the overall charge is going to be 0. So let's see, how am I going to word this? So second would be put the ions together. To add to the overall charge, which is usually 0 for what we're going to be talking about. All right, so let's try one that's not quite as trivial. What if we instead look at calcium and chlorine? If we want to make a compound between calcium and chlorine, we're going to do the same thing, figure out the charges. So what charge should calcium have? +2. And whether you write that as +2 or 2+, it doesn't really matter. Some books, some teachers differentiate between charges and versus oxidation states, which we'll get into a little bit later. I don't think it really matters. I usually always just stick to the writing the number first, just because then it's less confusing if you put it together with something else. It's clear that which thing that applies to, but you're free to do that however you want. +3 or +2 or 2+ or +2. All right, and then the charge in chlorine is the same as we just talked about. That's going to make that chloride ion. So how do we put those together to add to our overall charge, which is going to be 0? What do we need?
You need 2 chlorine.
Right, we need actually 2 of these because we've got 2+, so we need 2- to balance that out. So our overall charge on chlorine is going to be 2-. So we've got 2+ and 2-, which means if we put all those together, we can write that as CaCl2. So the formula between calcium and chlorine doesn't just take 1 of each. You need 2 of the -1 chlorides to balance out the +2 calcium. Yeah.
So is this when you're doing, like when you're like doing like ionic compounds, like you need to get it to 0?
Right.
Just in this case?
Right. Yeah. In some cases, we'll add to compounds that won't be 0, but almost always it'll be 0. Okay. Let's try another one. Try this one. So let's say we've got magnesium and oxygen. See if you can make a compound between magnesium and oxygen. What are the charges of each? And then how do you put them together? Everybody got it? What'd you get? You want to give it a try?
MgO.
Got MgO. So how'd you get that?
Well, magnesium has a 2+ charge, and oxygen has a 2- charge. So they just balance each other out.
Yep, everybody see that? So magnesium 2+, oxygen's 2-. So we don't need to adjust those ratios to get to 0. 2+ and 2- is neutral or 0 overall. So we put those together and just get MgO for our compound. All right.
Use how
Yeah.
you're figuring out the charges.
The charges we're getting from the periodic table.
Right.
So the first column are always +1.
Okay.
Second column are always +2.
Oh.
There you go. I think there's a thing in your book too.
It's back in chapter 2. Sorry.
No, it's right. This is in chapter 3. I can remember.
Here it is.
Oh, perfect.
So it's on page 65 of chapter 2, if you're wondering where those charges. Those are all the fixed charges that are always the same. In fact, why don't I pull that up here so everybody can see it if you don't have a book with you. What did I say that page was? 62? 65. Okay.
All right, thank you.
Yeah. They have this new book system. It sometimes takes a little while to get going. Okay, that's, who knows if that's going to work. Let's try again. Sometimes they have like, yeah, here we go. We'll get there eventually. put it right in the notes here so everybody has it. You see that? Okay, so those are all the ions with what we call predictable charges or known charges or fixed charges, the ones that always have the same charge. So however you need to remember those, that's how you want to do that. First couple columns, as we talked about, aluminum is 3+, kind of over by itself, and then the others that we looked at. Hydrogen is a little weird. It's not a metal, so it can be positive or negative. It's usually positive, unless it's with one of these metals, which are always positive. We'll get to some of those rules later, but these are the ones that you should always know. Okay. So that said, we'll just kind of leave this here. Let's try another one. What if we want to make a compound of aluminum and oxygen? See if you can build a compound from aluminum and oxygen. Anybody running into trouble on this one? All good? What did you come up with?
Aluminum 2, oxygen 3.
Yeah, so in this case, we've got aluminum's going to be +3. Oxygen's going to be -2. So you can't just change one of those. You have to change both of them in order to bring the charges in line. We need the lowest common multiple, or the least common multiple, which is 6. So if we've got 2 3s and 3 2s, we can put those together to make Al2O3. And that's going to give us a 0 overall charge, +6 and -6. All right. So you feel okay so far? I know this is new, but we're going to keep doing this. The only reason I introduced that first is where this comes up mostly is in the next part, which is naming. So if I give you a name of a compound like aluminum oxide, you've got to be able to write down what that formula is. And this is how you do it. You convert it to these charged ions, and then you figure out how they're going to match together, and you write them down that way. So we'll leave that for a second, but we'll come back to it very shortly. So why do we have to go through all these naming rules? Well, it's actually a simplification. It won't feel like that today because it's new and the rules get a little bit tricky. But basically, in the old days, you just had to memorize every name of everything. And it made chemistry like biology, which no one likes. So, you had to remember that this compound is called saltpeter, and this compound is called Epsom salts, and this compound is called, I don't know, a bunch of other ones. So grain alcohol is another one, or formic acid versus acetic acid. And these names didn't correspond to chemical structures. They were more about where they came from or what they were used for. So we needed a systematic way of naming them. And that's what we're going to go through now. I don't know why these things keep showing up. We need a systematic way of naming them so that if you say a name of a compound, everyone who knows the rules knows what you're talking about and isn't going to mistake it for some other compound. So in order to do this, we have to separate the compounds into a category. We're going to go through each category individually, and then we'll spend the rest of the day doing some practice of how do we do that? How do we actually physically practice that? So our first our first category are the binary ionic compounds, which are just composed of 2 elements. There's only 2 elements. Those are the ones we've just been practicing. Makes it a little bit easier because there's just 2 of them. Now, in those binary compounds, there's a few different categories. There's ionic compounds and there's molecular or covalent compounds. We're going to focus on the ionic compounds first. Within those ionic compounds, we've got 2 types. We're just going to call them type 1 and type 2. That's how your book describes them. And the type 1 compounds, actually both the type 1 and type 2, always have a positive ion, the cation, and then a negative ion, which we call the anion. The cation is always written first. So like the ones that we just talked about, these are things like NaCl, Al2O3, all the ones we just practiced on. You've got a cation, you've got an anion. There's only 2 types of elements. The cation is written first, the anion is written second. Cation is usually a metal. So to find these types of compounds, we're looking for metals, and we're looking for metals written first, and then one other thing. The reason that they are type 1 get this down here, versus type 2 is that they have a fixed, or what your book calls predictable, charge. So we know what the charges of the compounds are in these type 1 compounds. So those are all the ones we've just been talking about. We know sodium's going to be +1. We know calcium's going to be +2. So that puts it in this category. So here's how you name it. You've got a formula. You just say the name of the cation. Nothing changes. So sodium plus is called sodium. We don't make a different name between the positive ion and the neutral compound, even though they are very different. Sodium neutral compound is a metal, highly reactive with water. Sodium plus is a common ion in salt and in our bodies and everywhere. But then the anion is named by cutting off the end of it and putting ide, I-D-E. So instead of nitrogen 3-, instead of nitrogen, we call that nitride. Instead of oxygen, we've got oxide. Instead of chlorine, we've got chloride. Instead of selenium, we've got selenide. So they are predictable in that they always take that IDE. They're not predictable in that it's not always the same how they're cut off. So that's just something that comes with practice, and it's not something that I would mark wrong necessarily. Like if you called, let's say you wrote, I don't know, phosphoride instead of phosphide or something. Because how would you know how it was cut off? Yeah.
Or like, to see the rules of naming.
Oh yeah, we'll do that. This one, or like ones we already saw?
Yeah, that one.
This one, okay. So you name the cation first, then the anion. The cation takes its name from the name of the element, and the anion, the third rule. Can I get them all on screen at once? Yes. Well, almost. The third rule is that the anion takes the root of the element name and then adds ide. So cut something off the end. It's not sulfuride, it's sulfide. You get those? If anybody doesn't want to follow along rather than writing, by the way, this should update on Blackboard as soon as I save it each time. So it always puts the stuff that we're writing in there.
How do you find that?
It should be just in notes in like other course
Yep.
materials. Right there, yep. Go to today. There we go. Okay, so overall, we can summarize those rules in this little graphic from your book. Names of this type are going to be the name of the cation and the name of the anion plus ide. So let's do some examples. CaO, what are we going to name that? Using that rule. Calcium oxide, right. What about SrF2? Yeah. Yeah, strontium fluoride. And K2Se? You want to give that one a try? You can look it up in your periodic tables if you don't know the names. Yeah.
Potassium selenide.
Yeah, you got it, exactly, yep. Potassium selenide. So that's how that works. Now these are the easiest ones to name, but we also have to know that they go in that category. So let's review again, what are the rules that put them in this category, this type 1 binary ionic compound? What kinds of things are we looking for here? Yeah, the metal has to have a fixed predictable charge. So it has to be one of the ones in that periodic table graphic that we just put up. And you're looking for a metal and a non-metal together. Metal and a non-metal together to put them in this category. All right, with me so far? Okay, good. Yeah.
In the future, will we be able to refer to these things?
Yeah, I'm thinking about how to do that. I think for the summer, so the way that we do it during the year is up until the first exam, you can use these. After the first exam, you only get the symbols and no names. But because the summer is a little bit more condensed, I think we'll do that up to the second exam. So after the second exam, because the final exam is the National Standardized ACS exam, and they don't give you any names on that exam. So just as kind of practice and making sure you're good by then. It's also a multiple choice exam, so you don't have to just like pull the names out of your ass. You have, you just have to know which ones are which. Yeah.
Will we have like the charges, or like it's just gonna?
No, it's just like what's on the wall right there. Yeah. So you'll have the numbers of the columns, and you'll have all the numbers in the boxes, but no like charges or other things like that. And we're not going to take that off the wall, so anything there is always okay. Okay, so let's go into type 2. In type 2, the only difference, everything stays the same. The only difference is we have these middle metals that don't have a fixed or predictable charge. So let's see kind of where this comes from. So you've got iron, for instance, Fe, and I'm not going to say all these, you can read this stuff later, but iron can be in the 2+ or the 3+ state. It has two different common charges, which means there are two different compounds that could both be called iron chloride, FeCl2 and FeCl3. So we need a more specific name, so that if we say iron chloride, we know specifically which one of those two compounds we're talking about. The old way to do this was to use these suffixes, which maybe you've heard before. Ferrous chloride versus ferric chloride. Have you heard that kind of naming? I don't know. That was kind of the old way to do it. So you'd have like, that's where terms like nitrous versus nitric come from, ferrous, ferric. It was saying basically you have less versus more, that kind of a thing. Those get confusing because you have to use the old names for the elements. So instead of iron, we say ferrous because that's the old thing. Like there's all kinds of weird ones. Instead of copper, we'd say cupric. So again, it gets confusing because you just have to remember all these names. So now we don't do that anymore. You'll still see those names occasionally, but the way we do it is like this. We take this same naming system that we just talked about, and we add one piece to it. which is we specify the charge of the cation in Roman numerals and parentheses. So everybody remember what Roman numerals are? You know, they're like 1, 2, 3, and then 4 is IV. Is that, yeah, that's a thing. Okay, good. So that's the only difference here. The tricky part of this, or the only tricky part of this, is that the thing that goes in the parentheses is the charge of the metal. So the little, how many plus it is, not how many of them there are in the compound. And that's a really, really common mistake that I see. So if you have something like, let's say Cu2O, which is copper 1 oxide, the charge is 1, so it's copper 1 oxide, even though the little subscript is 2. You know, so we're going to do some practice and make sure that we don't get confused by that. So let's look at this iron example. If we have FeCl3, we have to figure out what the charge in that compound is. So we have to kind of go back from the ones that we know for sure and figure out the one that we don't. In the case of FeCl3, we know that chlorine is always -1. Chloride is always -1. So our Cl is -1, and we've got 3 of them. From that, we can figure out that the Fe must be +3 to balance that out. So if we've got 3 Cl minuses, then the Fe would have to be 3+ to balance that out, because there's just one of them. Compound's always neutral, so that's how you figure out the charge on the metal. In FeCl2, same thing. We've got still Cl-, but there's only 2 of them. So we need Fe2+ to balance those out. So the way we would write the name then is iron 3 chloride. Oh, this is talking about the old name, sorry. But we're not going to do those. So don't worry about this ferrous-ferric thing. Iron 3 chloride versus iron 2 chloride. I forgot I put this page in here to talk about those. But let's ignore that and just name these. So let's look at these other compounds of copper. So we've got CuCl versus CuCl2. What's the difference in naming those 2 compounds? They're both going to be copper chloride. How do we differentiate between them? Yeah, which one? Yeah, so the second one would be copper 2, and the first one would be copper 1. See how that works? Then the same thing with the next one with mercury. All right, let's look at some examples of how to do that. First of all, there are 2 exceptions that you should know, actually 3. Silver and zinc actually both count in that predictable charge category. So silver is always +1 and zinc is always +2. So we don't usually use the parentheses in there. Even though those didn't show up on that chart in chapter 2, there are those 2 more. There's a third one, actually cadmium as well, which is right under zinc, is +2. I will not be like really strict about grading that sort of thing because of those exceptions, but you should know they're there. So if you see zinc chloride just named without any charge, that's why. That's why it doesn't get Roman numerals. All right, we're going to go back to that in a second. But I want to get to, you know what, I don't see that here, so I'm going to just add it. Let's practice with what we've done so far. So we've got two different types of naming. The kind where there is a predictable charge versus the kind where there is not a predictable charge. I'm going to put a series of compounds here, and I want you to write the names. And I'm not going to tell you which category they fall into, type 1 or type 2. You've got to figure that out and name them. All right, so here we go. We got 4 compounds. I'm going to try to come up with names and then compare them to the person next to you or across from you or someone else. See if your names match up, and if not, talk about them and talk about how you got one name versus the other. If you want to go back and use your notes and look stuff up, that's fine too. If it's in that group, if it's in that area of the periodic table, one of those lists of those we put before, it's fixed. Anything else, it's not. So again, once you've got some names, talk to the people around you. See how, if they match up. If not, that's fine, just talk about it. If they do match up, that still doesn't mean you're right. It could be both wrong also, but see. Yeah, because you got to figure out, you know the charge of oxygen, but you have to figure figure out what the charge of cobalt is. It's not like you have to get it to 6 if you choose the formula. But you have to figure out what the charge of cobalt is. That would- All right, should we go through these? So what'd you get for that first one? Sodium nitride, yeah. You put any parentheses in there? No, because we know sodium is always +1. So that's a fixed charge. That's sodium nitride. What about the next one? Cobalt 203. What's the name there? Close. So let me write that down. Cobalt 6 oxide. That's almost right. Anybody see the issue there? Yeah, so you're actually looking for the charge on each cobalt rather than the total charge of cobalt overall. So if we calculate out this compound, we know oxygen is always -2, and there's 3 of them listed here. So that means the total negative charge is what for this compound? Yeah, total -6. So if there's 2 cobalts, what does each have to be to get to balance that out? Yeah, each has to be 3+, so that can be a total of 6+. So this one's what we call fixed or predictable. We know oxygen's always -2. We don't know what cobalt is, so we have to figure it out by knowing that the overall compound is neutral. Now, once we figure that out, then we can write in the number. In this case, it's the charge on each cobalt, not the total charge. So we call that cobalt 3 oxide. Each cobalt in that compound is going to be 3+, or 3+ charge. All right, what'd you get for the next one? You want to give that much? Titanium 2 oxide. Okay. Anybody agree, disagree? You want 4? Why 4? Yeah, so again, if we write out all the stuff we've got in this compound, we've got 1 titanium and 2 oxygens. Each oxygen is -2. So the overall negative charge in this compound is -4. So in order for that to balance out and be neutral, the titanium has to be 4+. So that works. The compound has to balance out overall. So if we've got each oxygen at -2, titanium has to be +4 to balance that out. So that gives this name titanium 4 oxide. Where that comes from? All right, what about the last one? Magnesium fluoride, yeah. This one, we don't use the Roman numerals because magnesium is always +2. All right, so that's the ways of naming ionic compounds. There's one more piece here that we need to put in, and then we'll take a break, and then we'll practice and talk about some of the other kinds of compounds. And that last piece is using polyatomic ions. Polyatomic ions are ones that are ions that have more than one atom in them. So things like ammonium hydroxide. The very first day, I think it was the first day or the second day, I gave you a list in the book and said, you just have to memorize those. There's not, I mean, there's some, I'm sure people have their own tricks of remembering them, but there's no chemical way of figuring out that NH4 plus is supposed to be called ammonium. You just need to know those names. Hopefully you know most of them already from your last chemistry class, and you just need to brush up on a couple of them. They are in the book. You have to let me grab that table, and I'll put it right in the notes again so that you have it. To do this thing again. The polyatomic ions, the good thing about it is there's nothing different in the way we name it. We're still using all the rules we just talked about. We only use those parentheses with those specific metals. We don't use those with different charged polyatomic ions or anything. The only tricky thing about the polyatomic ions is you have to know the names and the charges, and there isn't really a good way to kind of figure it out if you don't know them. So it's just something that needs to be memorized. I think the list of them is right here. Yeah. So let's put that right in our notes so that you've got an easy way of finding them. So for all these, you need to know the name, you need to know the charge, and the formula. So for instance, that first one, acetate, formula is C2H3O2, the charge is -1. So if you want to make flashcards or use a flashcard program on your phone or something to get these back in your head, if it's been a few years since you took chemistry before, please do that. So let's look at what those names look like when we use these. And if you don't remember all of them, you can look them up for now, or we can help each other out. Let's take a look at some of those. So what would that first compound be named? You want to give it a shot? Yeah. Yeah, so this one is ammonium hydroxide, made from ammonium and hydroxide. If you didn't know those ions, you'd think it was like nitrogen, hydrogen, 4, oxygen, hydrogen. I don't know how you would name that. But you just need to know that that's made of 2 ions, ammonium and hydroxide, by recognizing that NH4 is ammonium and OH is hydroxide. What about the next one? Go ahead. Yeah, so this one's going to be ammonium chloride. What about the next one down? Down a try. Close. This one is calcium carbonate. Bicarbonate is HCO3. What about the next one? Yeah. Ammonium nitrate. KNO3. You guys want to give that a try? So let's think about this one, because we just named the one before, ammonium nitrate. So what should this one be? Yeah. Potassium nitrate, thanks. Notice that our names, our naming rules aren't changing. The only thing that's changing is we're using the name of the polyatomic ion instead of something with an "ide" or whatever. But the cation first, then the anion, that stuff doesn't change. And then finally, this last one is going to be sodium sulfate. So those are all those type 1s. They just have polyatomic ions in there with them. What happens if we get the type 2s that also use the polyatomic ion? So let's look at something like CuSO4. We know Cu is copper, and we know SO4 is sulfate. But in order to name this correctly, we also need to know the charge on sulfate, so we can figure out the charge on copper. So what is the charge on sulfate? You remember that one? It's 2 minus. So what does the charge on copper have to be then? Has to be 2 plus to balance it out. So that means that our name here will be copper 2 sulfate. So the technique of naming, the rules of naming stays the same. The only thing that changes is we use the name of the polyatomic ion, and we need to know their charges. All right, let's stop there. We'll take a break. I'm going to bring in some worksheets, and then we will practice this when we come back. So we'll start up again in about 15 minutes. I'll leave this up so you can stare at it, try to remember them if you're here eating or something. So we've got a couple types of names that we've talked about so far. We've got the binary ionic compounds, type 1 and type 2, and then the ones with polyatomic ions that can also be in that type 1 or type 2 category, depending on the cation, depending on if it's a known charged metal or not. So let's look at the two other classes of names that we might encounter, and then we'll be done with the individual rules, and we can start practicing and start thinking about how we would put these things together when we actually need to name some things. Okay. So first of all, one way that we can help you memorize all those polyatomic ions, the oxoanions, the ones with oxygen, often go in this order: hypo, and then ite, and then ate, and then per with ate. So you've got that for chlorates, you've got that for bromates, iodates. It doesn't apply all across the board, but it may help you a little bit. If that doesn't help you and you'd rather just remember the names, just remember the names. All members of a particular category will have the same charge like that. So you'll notice they increase the amount of oxygen, but they keep the charge the same. Those are also on the list, I believe. So you can see them like here. All right, so the next category is the covalent compounds. And these are, we're going to talk about what covalent means when we get into bonding and electrons and all that. But from a naming standpoint, what you need to know is look for compounds that do not contain metals. That's really the key to finding things in this category. These covalent compounds are going to be almost exclusively nonmetals, so over on the right side of the periodic table. Of course, there's always some exceptions, but the ones we're going to encounter should fit into that quite nicely. So the way we name these is we actually specify how many of each element are in the formula. So for instance, CO we call carbon monoxide, like we're specifying that there is one oxygen. SiO2, silicon dioxide. You've heard these types of names before, right? Carbon dioxide. But there's a whole bunch of them. Now, most of them, there's actually a prefix on the first one as well. So if we look at something like N2O4, we would call that dinitrogen tetroxide. Let me make a list for you of the different prefixes. Here, comes back here. There we go. And then we'll practice them. So the prefixes are you only need to know the first 6. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 penta, and 6 hexa. So in these, when we don't have ions, we specify how many of each there are. So dinitrogen tetroxide. The couple exceptions to that is, like we say down here, if there's only one of the first one, you don't put a mono at the beginning, because otherwise there'd be way too many monos. It'd be hard to find stuff. We just start with carbon. So we don't call that monocarbon monoxide. We don't call it monosilicon dioxide. The way to remember that is just think about the ones you know. You know carbon monoxide. You know carbon dioxide. Like you've heard these names before. So that will help you remember that it's not monocarbon dioxide. It's just carbon dioxide. The other thing that happens is when there's a vowel, when the anion starts with a vowel, we usually cut one of the vowels. So like dinitrogen tetroxide, if we use the prefixes, it should be tetraoxide, but the tetraoxide kind of sounds awkward, so we cut off the A and just make it tetroxide. Again, when I'm grading your stuff, I'm not going to count you off for that kind of a thing. But when you're doing mastering chemistry, you'll get little messages if you don't have that right in there. For me, the key to all of this is communication. Can we tell each other exactly what kind of compound we're talking about? And the best way to do that is following these naming rules. So let's practice with the nitrogen compound. This also shows us why we need to name it this way. There are 6 different nitrogen compounds listed there. Those all exist. And they all have to have different names. They can't all be called nitrogen oxide. They're not ionic, so it doesn't make sense to put a charge in parentheses. So we need to name them in some different ways. The old common names are confusing. So we can just name them systematically. We can call this one nitrogen monoxide, this one nitrogen dioxide. What would we name that first one? Yeah, dinitrogen monoxide. We usually call that nitrous oxide, but technically, systematically, we should name that dinitrogen monoxide. Things that are really commonly used, unfortunately, their common old names do tend to stick around, so sometimes we'll see that. But we'll try to use systematic names whenever we can. All right, what about N2O3? You want to give that one a try? Yeah, go ahead. Close, yeah, dinitrogen trioxide for 3. And that one, we don't lose the vowel because trioxide sounds nice. So unfortunately, there's a little bit of experience there to just know which ones are which. But again, I won't mark you wrong if you call that something else. And then the very last one, you want to give that one a try?
Dinitrogen pentoxide.
Yep, you got it. Dinitrogen pentoxide. All right. Let's take a look at these 4. So with these 4 examples, I've not told you which category they're in. So we have to figure it out. One way we can do that is via kind of a flow chart. So I can pull this from the book here. Oh, it's all split up. Let's see. Well, it's all kind of laid out in a flow chart in the book, but let's just do it here. So the first thing we're going to look for is determine whether this is an ionic or a covalent compound. So our first question is, ionic or covalent? How do we make that distinction?
If it's metal or not.
Yeah, we look for a metal. What's the exception to that? What's an example of an ionic compound that doesn't have a metal in it?
Would you say hydrogen possibly be another peroxide be?
Well, it's actually, yeah, it's all of those polyatomic ions. So really what we want to look for ionic, we want to look for metals or those polyatomic ions. So if you see OH or you see SO4 or NH4. Those are those polyatomic ions. So you could have a compound like NH4NO3, ammonium nitrate. That's an ionic compound, but it doesn't have any metals in it. But as long as you know your polyatomic ions and you recognize NH4 or you recognize NO3, you should still be good. You should be able to see that it's ionic. Okay, so covalent is going to be nonmetals, not polyatomic ions. So once we figured out, so let's apply this then to that first one, A. Where are we going with A? Is that going to be ionic or covalent? And this is actually, I don't know why it's written that way. It should be P2O5. So is that going to be ionic or covalent? Does it have a metal in it? No metal. Does it have a polyatomic ion in it? No. So then what does that make it? Covalent. So it's got to be covalent. So we're off to that first step. Now there's another branch here that we haven't learned yet. But we'll get to that in a second. We'll just leave that there. So if it's covalent, how do we name it? Want to give it a try? Thank you. Diphosphorus pentoxide. Diphosphorus pentoxide. 2 phosphoruses, 5 oxygen. Now this method of naming the covalent where you put the prefixes, everybody likes that one because it's pretty straightforward. You find the prefixes, you put it in there. The danger is wanting to apply that where it's not appropriate, which is when there's a metal, when it's ionic. So let's look at the next one. So we got P2O5, the next one's NB2O5. Can we just call that diniobium pentoxide or pentoxide? Why can't we call that one then? Yeah, because now we've got a metal. Nb is a metal, it's right in the middle here. Is that a metal with a known charge or not? No. So that means we're in our next branch of our ionic flow chart here, where we ask, does it have a fixed charge or a predictable charge? In this case, we're over at the nose. So what do we do if we don't have a fixed charge? So we don't have a fixed charge here. So what is that name going to look like? It's going to be this kind of a form. It's going to have the parentheses, right? And the anion with ide. So how would you name that one? NB2O5. NB is niobium. O is oxide. So what goes in the parentheses? 5, yeah. We calculate that from oxygen. We know oxygen is -2. There's 5 of them. That's -10 overall. So that means each niobium must be +5 to get to +10 to balance that out. All right. C. This is a tricky one. I'll just warn you right away. What's tricky about this one? Anybody see something weird happening here?
It's ionic, but this just doesn't look like it adds up.
It's ionic, but it doesn't seem to add up. Why doesn't it add up?
Because the Li is added to +2, and the O is added to -4, so it has an overall charge of -2.
So does that mean lithium should be +2 here?
No. But
Lithium can be +2, right?
Yeah, but
So what's going on? Ideas?
it's an ion.
It's not wrong, but there's something else going on. Yeah. Yeah, O2 is actually a polyatomic ion. Let's go back up to our chart here. right here, peroxide, is O2, 2 minus. So,
Lithium peroxide.
yeah, so this is lithium peroxide. It goes into this category because the lithium does have a fixed charge. So we're just going to write cation and anion. If it's monoatomic anion, we're going to use ide. If it's polyatomic, we just list the anion. In this case, we had to recognize that that anion is actually peroxide. Now, what if that were a variable charge metal? What if instead of lithium, it were, let's say, copper or something? Could we still have figured this out? How?
You know the charge of peroxide.
We do, but how do we know that it's peroxide and not oxide in that particular compound? There actually isn't a great way of knowing that. So it doesn't come up a lot. There aren't a lot of peroxide compounds, but that we'll see. But generally, the clue is when they're with a known, it doesn't seem to add up like that, that's your clue that there's peroxide. And then finally, what would this last one fit into? So is it ionic or covalent? How do we know it's ionic? Yeah, titanium. Well, yeah, or there's a polyatomic ion. Yeah, both. There's a metal, there's a polyatomic ion. So which category does it fit into? Fixed charge or not? Fixed charge or variable charge? Yeah, variable. Titanium is going to be one of those ones in the middle. So that means we're going to have titanium something, and then what's that anion called? That is nitrate. What's the charge of nitrate? -1. -1. So if the charge of nitrate is -1, nitrate is NO3 -1, what does the charge of titanium have to be to balance that out? Has to be 4, right? Because there's 4 nitrates, 4 -1 nitrates, so we need a +4 titanium to balance that. All right, sound good? All right, let's put the last piece in, and then we can practice all these different fun ones. Okay, our last piece is acids. So our last branch is going to be of the covalent compounds. And actually, there can be some metals in here too, so it's kind of its own category, which is why we're doing it at the end. There are the acids. There's one great way to determine if you've got something that you need to name as an acid. Anybody have a guess based on all those that are listed right there?
It's hydrogen in the front.
Yeah, hydrogen in the front. That's what's going to be our clue that we've got an acid. There are very few compounds that start with hydrogen. We'll talk about a couple of the exceptions like water. But most of the ones that are starting with hydrogen are going to be named as acids. So there's 2 types of acids. There's the ones that are binary or sort of binary, which are the ones listed here, where you just have H and then one other ion. These are the ones you've probably heard of, like you hopefully know that HCl is hydrochloric acid. So using that same type of naming scheme, what would HBr be? Yeah, hydrobromic acid. And what about HI? Close, yeah. We're hydroiodic acid. What about H2S? This one's a trick question. This is not named as an acid. This is hydrogen sulfide. So, sorry, that one's hard. But again, there's just a few weird ones like hydrogen sulfide, then you've got water, others in that group. Ammonia would be another example, although we don't list the hydrogens first. And what about HCN?
Hydrogen cyanide.
Yeah, that one's going to be, well, actually, hold on. Try again.
Like hydrocyanic.
Yeah, there you go. That one actually is considered an acid.
What's hydrogen cyanide? I've heard that before.
Probably just another way to name this.
Okay.
Okay, so when there's just H and then one other thing, or with CN is kind of a weird one, it's hydro whatever acid. Most acids form into this other category where the anions contain oxygen. So you've got hydrogen with some number and then something with oxygen. So H2SO4, HNO3, those kinds of things. These get a little bit trickier. The only trickier thing is this. If the anion name ends in 8, then we make the suffix "ic" to name the acid. So H2SO4 contains SO4 2- anion. That anion is called sulfate. So to name that acid, we're going to drop the 8 and put on "ic" and call it sulfuric acid. If there's an ite, like HSO3, which is sulfite, then it gets an OUS ending, and it's called sulfurous acid instead. The best way to remember these is remember a couple of them, and then try to figure out the other ones based on that. So like sulfuric acid, that's a common acid that we use all the time. We should all know that sulfuric acid is H2SO4. So that way, if you need to go back and figure this rule out, you can think, okay, well, H2SO4 is sulfuric acid. SO4 is sulfate, so the 8 must go with the ic. So if you forget, at least you know some of the common ones. You can also do that with nitric acid, which is another common one that we use a lot. Nitric acid is HNO3. So if you just know that one, you can figure out the rule if you get some weird one. So let's take a look, speaking of some of the weird ones, at some of these oxo anions of chlorine and their acid counterparts. So how would we name, let's start with the first one. That anion is called, ClO4- is called perchlorate, which you'll all know once you memorize that chart. So what is the acid HClO4 called? Yeah, you drop the end and you just put ic. So this becomes perchloric acid. Notice there's no hydro on the beginning. That only applies to those couple acids that we talked about before. Most other acids go like this, so perchloric acid. What about HClO3? Chlorate, so what's that acid called? All you got to do is change the suffix. You wanna just shout it out.
Chloric.
Chloric, thank you, yeah. All right, next, chlorite becomes, yep. And finally, yeah. So another common one we might use, or we will probably use. Oh. Can we name that one? HC2H3O2. What's that anion called?
Acetate.
That is acetate.
Acetic acid.
So that is acetic acid. All right, so that is all the rules. Let's fill in our flow chart up here. Once I get my computer back here. So our last piece here is going to be on the covalent side. We have to see if the name, I got a room, so I'm just going to do it over here. Does the name start, or does the formula start with hydrogen? If yes, we're going to use the acid rules. If no, we're going to use the regular prefix rules. I don't know how to make that short, but we'll say like prefix rules, you know, that the di, tri, tetra stuff. So that's our full way of naming. All right, so now you've got a lot of practicing here. Nothing is sorted into categories on this sheet. They're all mixed in. So they could be ionic, they could be covalent, they could be acids, they could be variable charge, they could be fixed charge, they could have polyatomic ions, they could be binary. There's a bunch of practice of everything. So let's try in your groups, see if you can figure out this first side, this first page. So 1 through 24, they alternate. Either you're writing the formula from the name or the name from the formula. When you write the formula from the name, you got to go back to the stuff we did at the very beginning where you match up the charges. So work together. Move around if you want to work with other people than who you're sitting with, and see if you can figure out that first page. Call me over if you're stuck. That's not cool.
I'm just saying, where can I find the sheet that has the, like, see, like,
It's right in the notes. So
where the notes, I'm looking for them, I can find them.
Yeah, so I put them in the notes today. It's also in the book. There's a table in the book. You can also just look up polyatomic ions. Polyatomic ions, and I'm sure there's a lot of stuff out there.
All right, because I didn't know, like, didn't know he had the notes, like, on.
Yes, the notes are on Blackboard.
Right, they were already on Blackboard, is it like fill them in? That's my question.
No,
That's because I thought, I don't remember that, but not filled in.
we just put that in right now, so it's there now.
So now they're there.
Yep.
Okay, thank you.
Oh, you don't. No, you don't. You just figure it out. This chloride's always going to be minus. So this has to be lead too, whether or not that's actually possible. There are some in this chart that are in this exercise that are not on the chart, but they should be very similar to other ones on the chart. So see if you can figure it out.
Number 2.
SO2. None of your SO2s. Oh, wait, there's. Oh, yeah, you're right, that's all I forgot. Yeah. Yeah.
Because you know the chloride, and so you assume that the sand is there.
Okay, that's for the end.
And if it turns out not to be, there's no way you could have.
You could figure that out. Okay, that's what you, I
Yeah.
was like, I could do that, but that doesn't feel right.
It's so. As you're going through this, put a little note next to ones that were particularly difficult or that you just could not figure out or that you got wrong and you can't figure out why you got it wrong. Well, if you're looking up the answers, if you don't like the answers, it's fine. So then we can go back to that and try to figure out if there's particular types of compounds that you can use not today. Once most groups are done with the first side, we'll go through the answers.
So if you want this for reference, I'll leave this up here. Maybe.
Yeah, then if it work that way, then there'd be no way to go. So we have to. Yes. Yeah, that's correct. Yep. Right. So there's two of those holes.
Yeah, these ones, okay.
And then we'll do the charge.
I know there's a couple more rows here, but this thing kind of crashed and froze, so it's just stuck there.
Yay.
I don't know. I could shut it down and try to reload it or something. I guess I could do that. Okay, there we go.
If you, I know first I go ahead and start on the second. Still working, so we'll go a few more minutes before. The answers. Okay.
Number 50, I'm just like, what the, is it really ammonium fluoride?
No,
I didn't think it said.
that's another polyatomic ion. It's not on the list. It's called phytosine.
So ammonium fluoride. Thank you, because I was like, that's all I didn't think that was right. It's not normal for something that three terms.
It's gotta be a polyatomic.
I mean, it's technically, it's like if we were doing something different, like we were doing more common things, maybe that's possible. But I didn't think so, sorry. Thiazide? Alright.
If it's into a different category, then the way you're trying to make it. Right. Yes. So how do you name an acid that's made from a sulfate? Close. It's just sulfuric acid. You only put the hydro first if it's just one thing, like HBr or HCl.
Oh, yeah, so hydrosulfuric acid is H2.
No, that doesn't exist. It's not.
Then what the heck is hydrosulfuric acid?
It's what?
Hydrosulfuric acid.
It's not a real name.
So 31 is 31.
Oh, yeah, right. So that would be that would be H2. Oh, no, it's not actually called that.
Okay, so
But that's what it would be called that.
For this one, so I originally had a little before, but I haven't how to figure out the value for this.
What's the charge when it's phosphate? Yeah, right. So if you find phosphate is like on the left, so it's 3 minus.
Okay.
So then that's.
Okay, yeah.
All right, let's take a look at some of these. Whether or not you're done, it's fine. You can keep working. You can listen. You can have work. You can listen. Whatever.
Oh, I don't have this up here. Okay, so we'll just talk about it over here. All right, so aluminum chloride. So what I'm going to do here, I'm just going to tell you the answers. And you stop me and say, hang on, whenever you want me to go through how we get that. Either the name or the formula. Just say, how do you get that one? Or just shout it out if I'm not looking up. And we'll go through that one. So aluminum chloride is AlCl3. You want to go through that one? What's the charge on aluminum? Always +3. So you need 3 minus 1 chlorides to balance out the +3 aluminum. Does that make sense? Yeah. All right, number 2, the formula is MgCO3. So the name is magnesium carbonate. 3 is a little bit tricky, perbromic acid. Anytime we see a per something acid, we know that comes from the per8 anion. So this must come from the perbromate anion. But that's not one that's on the chart. So how would you figure that out?
Compared to the chloric acid?
Yeah, anything in the same group, in the same column of a periodic table should be pretty similar. So we know chlorate and we know perchloric acid. So we can probably assume that bromine is going to be the same. Now, if it turns out not to be, there's nothing we can really do about that. There's no way we would have known. But that's the best guess we can make. So we have to guess that this one is HBrO4, because if it were perchloric acid, it would be HClO4. All right. 4 is going to be lead to chloride. We should also note here, element names and ion names and compound names are not proper nouns, so we don't capitalize them if they're just in the middle of a sentence. 5, dichlorine oxide should really be dichlorine monoxide. That would be Cl2O. That name is not quite right. 6 is copper 1. Nitrate. Nitrate is a -1 anion. So if there's one of those for 1 copper, it's got to be copper 1. 7, potassium phosphate, K3PO4. Again, you look at the chart. Phosphate is a -3 anion. So that means we need 3 of the +1 potassiums to balance that out. Eight is going to be iron 2 hydroxide. Hydroxide is -1. There's 2 of them in this question. So that means there's 2 minus overall. And we need +2 iron to balance that. So iron must be +2. 9, sodium hydrogen carbonate. NaHCO3. Hydrogen carbonate is also called bicarbonate sometimes. 10. This one can be tricky if you don't put it in the right category. So H2SO4, which category does that belong in? It's an acid. So we have to recognize that because the H's are first, that needs to be named like an acid, not like a covalent compound. So that means we call this one sulfuric acid because SO4 2- is sulfate ion. So sulfate becomes sulfuric acid. All right, 11 is calcium bromide, CaBr2. Again, stop me if you want me to go through these. Iron 2 bromide, 13. That's a covalent compound, so we just write it. Now be careful with 14. 14 is NO2. What do we call that? That's a, well, which category does it fit in? Yeah, that's a covalent one. So that's going to be nitrogen dioxide. Why isn't it nitrite? Because of what? Yeah, so this can be confusing sometimes because on this chart we see NO2 minus is the nitrite ion. But on the sheet it says NO2. So why don't we call that nitrate? Because that's not an ion. That's a neutral compound, the one on the sheet. So the one on the sheet is named nitrogen dioxide. It's a neutral covalent compound. It's only nitrite when it's a 1 minus anion. Oops. So 15, lead 4 chloride. Was anybody tempted to write that lead with a little 4 and then Cl? That's a mistake I see sometimes too. The parentheses, remember, indicate the charge, not the number in the formula. 16 is silver chromate. We don't need the parentheses there because silver is always +1. So that's one of those exceptions with the fixed charge. 17, copper 1 oxide. Again, don't be tempted. That formula makes it look like you want to call it copper 2 oxide because of the little 2. But the charge on each copper atom is 1, not 2. So we actually call that copper 1 oxide. (18) Lithium is a fixed charge. If iron is +3, then we need 2 of them for 3 oxygens. So that makes iron 3 oxide. Mercury 1 chloride. Dinitrogen monoxide. Again, it should be monoxide, not oxide. That's a mistake on the paper here. Anybody know what that compound sodium hypochlorite is? Also known as NaClO or NaOCl. That's bleach. And this last one was pretty tricky. That's not an ion that's on the list, but we do see hydrogen phosphate and dihydrogen phosphate. So if we see PO3 instead of PO4, we can assume that it just changes to ite. And so that's what you can get last. Yeah.
Wait, for 20?
Yeah.
Why'd you do like mercury 1?
Yeah, good question, because there's 2, because it's Hg2Cl2. So each mercury gets +1 because each chlorine has to be -1. The reason that's written that way, it's kind of a weird compound where the mercuries actually form these little dual diatomic molecules within the ionic framework. So the ion is kind of 2 mercury atoms together, but each one then needs to be +1 because each chlorine has to be -1.
So there's no such thing as like mercury 2.
There is, but that would be HgCl2,
Oh,
not Hg2Cl2. So HgCl2 would be mercury 2 chloride.
yeah.
Hg2Cl2 is mercury 1 chloride. That's weird because you'd think mercury 1 chloride would be just HgCl. So that's a weird one. Yeah. All right, so that's the first page. We got about 20 minutes to go. So if you want to stick around and keep working on the second page, and you know, I can come around and help you with those, that's good. If you feel good with this or you went through that and that's fine, you can go and I'll put the answers up on the notes if you want to check them later. Tomorrow's lab, so please read the lab and be prepared with any pre-lab activities. I think we're doing density tomorrow. And what else? So the quiz on this stuff will be next week. So you've got until next Monday to get these names and all this stuff down. We'll practice more on Thursday in class also. What? We're not spending a whole week on this. Thursday we're going to get into chapter 4, but we will also practice this. Yeah. Oh, okay. I'll come on over. So if you're sticking around, go through and keep working on this. Otherwise, I'll see you tomorrow. Okay.
Oh, this is chapter 2. Yeah, chapter 2 is up to the end. Oh, because you got to do it. So,
It's always due lab. All right, so let's see what's up. So you got your stuff here?
Well, how did you?
So I got mine off of Amazon.